MO theory, molecular orbital theory, for aromaticity. Now, in benzene, we have 6 p orbitals that get combined. And of course, if we make 6 p orbitals, by conservation of orbital symmetry, we have to make 6 pi MOs. Okay. It's no different than if we combine an S and 3 p orbitals by conservation of orbital symmetry, we make 4 sp3 orbitals. So it turns out that for aromatic compounds, these go in a particular order. And there's some nice pictures in your textbook, and I encourage you to look at some of those figures and understand them. But at the undergraduate level, I'm not going to ask you to regurgitate those MO pictures. But what I do want you to be able to do is to understand the energy levels for this. And it turns out there's a very quick and convenient way of doing this that actually tells us how Huckel arrived at Huckel's rule. And this is called Frost's circle rule. Okay? So we take whatever normal geometric polygon would correspond to our molecule. So in the case of benzene, we take a hexagon, a regular hexagon, and we circumscribe it with a circle. And you're going to see why I'm in the science department and not in the art department here. Okay? Now, everywhere that a vertex of this system touches the circle, we will get a corresponding energy level. So the point that would correspond to the equator is our non-bonding level. And we will have an orbital of lowest energy. There's the +2 from our Huckel rule. And then we find that at every other energy level as we go up from that, we get 2 orbitals. Now, how many electrons do 2 orbitals hold? 2 electrons, 2 per orbital. 2 orbitals, 2 times 2 is 4. Look at that. Math is useful after all. Then 2 more, and then for benzene we will have 1 orbital of highest energy. These are the relative energy levels, and so energy is increasing in this direction. Now if we consider benzene, benzene had how many pi electrons? 6 pi electrons. And so we will begin to fill, Hund's rule from Gen Chem, fill the bottom orbital. Next, 3 and 4, we put 1 in each of the orbitals that are degenerate in energy, and then 5 and 6. And so we see for benzene that all of our bonding orbitals are filled and all of our anti-bonding orbitals are empty. And so this gives us a very stable electronic configuration. Now let's contrast that to maybe I'll just move over here. Let's contrast that to a square version of cyclobutadiene. Now, cyclobutadiene is a square, so to draw a Frost circle, I need, again, I'm not very artistic, so I'll draw my square here with 1 vertex down If I imagine circumscribing that with a circle, of course, these two at the center here are at the non-bonding level. We'll have one orbital of lowest energy. We'll have a pair of degenerate orbitals that are at the non-bonding level and one anti-bonding orbital. Now, butadiene had 4 pi electrons. Now we learned from our criteria that this was an anti-Huckel number of electrons. Let's see what happens if we consider our hypothetical square cyclobutadiene. We start to put in the electrons, 1, 2, and then following Hund's rule, 3, 4. That's all of our pi electrons. So if cyclobutadiene is a square, it will have this electronic configuration where we have 2 unpaired electrons. E minus is just electrons. And of course that means that we have a very reactive and unstable species. Turns out that this undergoes a type of what's called a Jahn-Teller distortion. Jahn-Teller distortion. I won't get into the details of that in this class, but for you to know, Jahn-Teller, that chemist Teller, is actually the same Edward Teller of the hydrogen bomb. This distorts, as I told you earlier, into a rectangle, and now the electronic configuration is I have 2 bonding orbitals and 2 anti-bonding orbitals. And so when I put my 4 electrons in here, I fill the bonding and I don't have anything in the anti-bonding. So this is the orbital picture for the real. Get a pen that's going to write for me now. Cyclobutadiene, because it's really a rectangle. But you can see from the MO picture, if it were a square, it would be this highly reactive and therefore unstable species. So this is the MO theory that helps us understand aromatic compounds and their special stability. And you should be able to explain things on the basis of the molecular orbital theory and Frost's circle.